Hi everyone. In this video we're going to go through the answer to the questions here. We'll be drawing Lewis structures, naming molecular geometry, and then identifying whether the molecule is polar or non-polar. So the first step of drawing Lewis structures is to count your electrons. So we have tellurium here, and we have 6 electrons in its valence shell. Fluorine brings 7. There are 6 of those. So we have a good number of electrons here, 48 electrons. And the next step would be to build our framework. So I'm going to put all of those fluorine atoms about that central atom. And this is going to be common for when we have 2 types of elements. We used 12 electrons in bonds, so we have 36 left over for lone pairs, and that works out nicely. Each of the 6 fluorine atoms will have 6 non-bonded electrons. So we've used them all. This is the structure for tellurium hexafluoride. And at this point we need to consider the geometry. So with 6 groups around it, the molecular geometry, the electron domain geometry would be octahedral. And since none of those groups are lone pairs, the molecular geometry, considering only the bonded atoms, will also be octahedral. And from here we can think about whether or not we have polar bonds, and we do. We can more accurately draw the groups here with wedges and dashes. So I'm going to go ahead and erase the bonds in my plane and draw in so we can see more three-dimensional picture here. And so if we look at this now, all of these bond dipoles will cancel to yield a non-polar species here. So that's a nonpolar compound. With the octahedral geometry, all of the bonds are polar, but there's no net dipole because they all cancel. Now for selenium tetrafluoride, we have 6 valence electrons with selenium, 7 in fluorine again still, and 4 of those. So we have 28 plus 6, that is 34 electrons. So I'm going to build my framework. And then subtract my 8 electrons. So I have 26 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And that last pair will go on that central selenium atom. So now that tells me, if I look at selenium, my steric number is 5. So my electron domain geometry for 5 is trigonal bipyramidal. And since one of those groups is a non-bonding pair, a lone pair, we would not see that in the molecular geometry. And so my molecular geometry will be different. Now, let me draw this differently here so that you can see what the square planar geometry would look like. Okay, that lone pair is going to prefer to be in an equatorial position, such as to maximize the space that it has, because this angle is 120 degrees. And as such, we won't see that in terms of the molecular geometry, so we can just get rid of it. And that means that my molecular geometry, as we can imagine this, is known as seesaw. So turn that on its side 90 degrees, and you have the base of the seesaw here, and that's where that name comes from. In terms of my bond dipoles, we have a pair of opposite dipoles here on the axis, so those will cancel, but the dipoles shown on the left side of the structure would add to give a net molecular dipole in that direction. So this is a polar molecule. And the last example is xenon difluoride. We have 8 electrons from xenon, 7 times 2 is 14, So that's 22 electrons. Xenon will be my central atom. I'm going to put 18 electrons as pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so my central xenon atom has 5 groups. This is going to have trigonal bipyramidal geometry again, just like the last one. And all of those lone pairs will want to occupy the equatorial position, so they will kind of be as drawn here around that equator, resulting in a molecular geometry that is linear. And because of that linear geometry, these fluorine atoms are going to be pulling opposite one another, yielding a nonpolar molecule. So, if we follow the steps for drawing Lewis structures and we consider how these molecules look in 3 dimensions, we can determine whether or not a molecule is polar based on whether or not the bond dipoles cancel or not. Thanks for watching.